Okay, now let's look at La Nina. Write in your notes that La Nina means the little girl in Spanish, and that La Nina episodes represent periods of below average sea surface temperatures across the east central Pacific Ocean near the equator. Also write that the effect of La Nina conditions are frequently the opposite of those of El Nino conditions. Get in your notes that in the tropics, ocean temperature variations in La Nina also tend to be opposite of those of El Nino. And that during a La Nina year, winter temperatures are warmer than normal in the southeast and cooler than normal in the northwest. Okay, so let's just give a quick review of the difference between El Nino and La Nina, just so we understand these conditions. So let's get them in your notes. So let's talk about the characteristics of El Nino first. So write in your notes that a large pool of warm water is located at the central and western part of the Pacific Ocean. So here we go, the central and western part of the Pacific Ocean. Atmospheric conditions can increase the temperature of the surface water. And as a result, this pool of warm water enlarges and shifts eastward to cover the tropics. Also write that El Nino causes a decrease in the eastward flow of the trade winds. Now, on the eastern side of the Pacific, parts of Australia and New Zealand and the Philippines and Indonesia experience drought conditions. Make sure you have that down. The effect can spread as far as India. Now, the opposite happens in North and South America, where the general climate conditions are wetter and warmer. So when we're in an El Nino, we have wetter and warmer winters, which means we can have some snow still, but the temperatures would be higher, much warmer. This year is not an El Nino year, obviously. We're getting extremely cold temperatures, not nearly as much snow as we would in an El Nino year, where it's much warmer than it normally is. Now, characteristics of La Nina. The large pool of warm water in the Pacific shrinks, write this down, because the east trade winds strengthen and carry colder surface water from the east to the west. This reduces the overall temperature of the surface water. Now, on the western side of the Pacific, rainfall is generally heavier than normal, but on the eastern side, the rainfall is reduced with cooler temperatures. That's us. So La Nina is exactly the opposite of El Nino. In El Nino, we get warmer and wetter. In La Nina, we get cooler and drier temperatures. So you need to know the difference between those two. Now let's turn our attention to ocean waves or large lake waves. The characteristics are not that much different. And we'll try to correct some misconceptions about these waves and what causes wave action. Now first, write in your notes that a wave is a disturbance which moves through or over the surface of a fluid. Remember, a fluid can be a gas or a liquid, and is most often caused by winds. Now, just a quick review of some wave characteristics to get in your notes. First of all, yes, get this diagram in your notes and be sure to label it correctly. I know you love those. Notice the still water level. This is where we're going to start. The still water level. Write in your notes that this would be the water level with no waves. When water, we call it like flat calm or a calm surface. So there would not be any of these humps and troughs the water would be still, which would be straight across. Write that the crest is the distance from the midpoint of a wave to the highest point in that wave, while a trough is the distance from the midpoint to the very bottom of it. So here's our midpoint, we call the still water level. And now this distance from here to here is called the crest, and the distance from here to here is called the trough. Now, write that the crest is the distance from the midpoint to the highest point in the wave, trough is the distance from the low point, and that the height of the wave is the distance from the crest to trough of a wave, the crest to trough, so the height of a wave is from here to here. Here's that whole distance. That is the wave height. And that wave length is the distance from crest to crest. So here you see from here to here is the wavelength, or trough to trough. We only see one trough, but if we could draw this line down here, the distance from trough to trough would also be called the wavelength. So get those all in your notes. Wave height is affected by three factors, and I'd like you to get them in your notes. The first factor is wind speed, or how fast the air is moving. The second factor is wind duration, or how long the wind blows. And finally, and this will be a new term, is the word fetch. Here's the word fetch. Fetch is the distance over water that the wind blows in a single direction. All right, the distance over water that wind blows in a single direction is called fetch. This then sets up four conclusions about waves that we also want you to get in your notes. So we've written three factors that determine waves. Now let's write four conclusions. Conclusion 1. If wind speed is slow, only small waves result, regardless of wind duration or fetch. So if wind speed's slow, these are going to be small waves regardless of how long the slow wind blows or the distance that it blows, called fetch. Conclusion 2. If wind speed is great, but it only blows for a short period of time or a few minutes, no large waves will result, even if the wind speed is strong and fetch is unlimited. So the time's low, you're not going to get big waves either. They'll, for lack of a better word, peter out. Conclusion 3. If strong winds blow for a long period of time, but over a short fetch, no large waves form. So, if strong winds blow for a long period of time, but over a short distance, no large waves form. And then our last one, our fourth conclusion, large waves occur only when all three factors combine: high wind speed, long duration, and long fetch. Also write in your notes that as waves develop, they offer more surface area for the wind to press against. So if we look at this in this way, the larger these waves get, the more surface of the water there is for the wind to press on. So as these waves get bigger and the chop gets bigger, the wind has more surface area to blow on. We call this wind stress. Get that in your notes. So, let's get the wave progression steps in your notes now. So we've gotten the factors, we've gotten some conclusions. Now let's get the wave progression steps. So, number 1, as waves develop, they offer more surface area for the wind to press against. Now, waves start as micro ripples, you see them here. So imagine now our flat, calm water. And then we now have a wind that's going to blow for some duration over a period of time. If you look from the lee side of the lake, the lee side is the calm side, you now can see micro ripples start to form as we move across the lake or the ocean. Okay, so these micro ripples form next. Now, there's not much surface area, but as the fetch increases, ripples form, which are now larger. Then chop forms, which are larger still, which gives a tremendous amount of surface area for the wind to blow on now. And then now from chop, we go to what's called a fully developed sea, which now you've seen before. If you've gone over the Mackinac Bridge on a relatively windy cycle, you've seen these waves develop. And the same thing happens now on large ocean bodies of water. So that's our progression now. Micro ripples, ripples, chop, fully developed sea. And the surface area has everything to do with why that happens. Okay, now for the misconception. Right, that most people believe that waves actually make water move great distances. In other words, that waves move water from point A to point B toward the shoreline. This simply is not true. Write that in deep water, and you see the example of it right here. Here's our bottle now. Bottle's in this location, and notice that it's not moving. Write that in deep water, a wave is a forward motion of energy, not water. And in fact, the water does not even move forward with the wave. Now, if we follow this single drop of water, that's what we have here. Here's our single drop of water. If we followed a single drop of water during a passing wave like you see here, we would see it move in a vertical circle like you're seeing it move here. So it moves in a vertical circle, returning to a point near its original position at the wave's end. Now these vertical circles are more obvious at the surface, and you see now a picture of them right here. So it's a series of columns now of vertical circles that happen. So the conclusion I want you to write in your notes is that it's the actual energy wave we see moving in a lake or ocean wave, not the water particles themselves. Let me say that again. So it's the actual energy wave we see moving in a lake or ocean, not the water particles themselves. And here's a perfect example for you to get in your mind. That bottle's not moving. It's just bobbing up and down, and it's bobbing up and down because of these water molecules. Water columns, excuse me. That's kind of a weird name. I don't think it is a word. Okay, let's finish with some important functions of the waves we see in large bodies of water. First, write that waves help to shape our coastlines by eroding cliffs and grinding rock into sand so it can be recycled. You see a picture of it right here. Then write that waves also help to return needed breathable oxygen to the water while also stirring up food for the filter feeders in that body of water, like the clams you see here in this picture. Two extremely important functions of waves. Okay, that's it for our discussion of oceans and what they do to help shape our climate. So take a picture of your notes, submit them to Moodle, grab that last ocean study guide, answer the questions, and I'll see you back here in our next section, which I'm going to make you guess about. Bye.